So here's the big umbrella idea of optimization theory, and that is that inside the database, there are inherent dependencies between the schema, set-based code, indexing, concurrency, and then advanced scalability. And the best way to optimize your database is to take advantage of these dependencies so that you really enable the layer you're wanting to work at. So optimization theory is a framework for performance and a way to understand and repeat good performance from one project to another. It begins with the schema, and the best practices of optimizing the schema is to completely fear overcomplexity. I've seen so many schemas that are so complex that it becomes impossible to write set-based code. Use good agile schema design, meaning lots of iterations and a team trying to really figure out the best way to have the schema. And then to analyze the schema for performance instead of only data integrity. In the schema, use generalization to avoid having too many tables. I avoid denormalization, and I use denormalization only in a few key areas. Avoid making your schema where you model negative attributes and you model only positive attributes, where a row means something exists rather than a row means something is not present. Always make sure you normalize, and use situational modeling that we talked about in the relational database design lesson to make your primary keys fast. And be careful about how you design for optional data. My first recommendation is to use a nullable column, but surrogate nulls are acceptable if you can be consistent about them, which is the trick, but avoid at all cost the missing row pattern. And lastly, enforce a good abstraction layer to protect the schema, to encapsulate the schema. This is the only way to have long-term extensibility so the database is flexible and you can make changes without having a domino effect, breaking tons of code. This logical abstraction layer could be implemented inside stored procedures and views or in some kind of layer above. I personally prefer doing it in stored procedures because only then can the abstraction layer be truly enforced so that ETL processes, extract, transform, load, and reports, and every other thing that connects to the database can always use the abstraction layer. An abstraction layer that's there only for the front-end client but ignored for all reports and ETL processes is not truly an abstraction layer. So if you have a nice clean schema and you've avoided overcomplexity, then it's easy to understand the schema. It's obvious on how to query the schema, and you will set yourself up for writing good set-based code. But I've seen schemas that are extremely difficult to query and almost force you to write cursors in clumsy code. And set-based code can't overcome a poor schema. I've seen schemas so bad that it's nearly impossible to write good set-based code. So this is the dependency between schema and set-based, that schema enables or sets up set-based code. Within the layer of set-based code, there are several good key best practices. Use the right solution. Avoid cursors. Understand how query plans are reused, and design your set-based code and stored procedures for reuse. Many times, developers have trouble writing set-based queries because they don't really understand how to use stored procedures. So it's key to understanding the stored procedure lesson from part 2. And here's a list of some types of problems and what I recommend to solve them. So if you're doing complex business logic, use queries, subqueries, and CTEs, user-defined functions to solve these. To denormalize a list, use a multiple assignment variable. For crosstab queries, use pivot or case expression. Avoid using the correlated subquery for crosstabs. For navigating hierarchy, I recommend using the UDF. For cumulative totals, use a cursor. Avoid the correlated subquery method. The cursor will scale so much better for cumulative totals. And then another time when cursors are useful is when you have to build dynamic code that will iterate over DDL, manually creating tables and things like that, but that's rarely needed inside of a normal application. Avoiding cursors. And this is a test that I did where horizontally 1 through 10, the data changes with the same amount of new data added with each iteration. And you can see the time vertically on how long it takes to solve this problem. And this is simulating a complex business problem with multiple formulas and multiple exceptions, going through and updating the data based upon a very complex formula. The lines that scale poorly are the cursors. The update cursor, fast forward cursor. The best performance was from the query with a case expression, followed by a query with an embedded function, followed by a multiple queries. And if you want to download and see all this code, it's available on my website, SQLServerBible.com. So if you have a complex cursor and you want to refactor it to set-based code, here are some ideas. Use a multi-statement, table-valued, user-defined function to embed the logic within a set-based query. A great idea, if you can pull it off, is to use a case expression so your logic can be flexible and can function differently for different cases, for different values in different rows. And then avoid hard coding by using a data-driven database design. And although it's a brute force method, it works very well to simply break the task up into multiple queries and let the where clause of the queries determine which rows function for different types of formulas. So, if your schema is clean and you've set yourself up for set-based queries, that will enable you to do good indexing. In fact, it's easy, it's a pleasure, it's a joy to index when you know what the set-based code is and if you have a nice clean schema. But indexes can't overcome cursors or iterative code. If you simply have a lot of scattered code all over a VB application, it's difficult to understand how to index. And of course we can use Profiler to go and capture all of that. But the worst time to index is when you have an extremely overly complex schema, a design that possibly could have been done in 30, 40, or 50 tables that's been overly normalized and is being done in 400 or 500 tables. Extremely difficult to index that.